move on to our next talk, which will be talking about a small topic, planetary volcanoes, particularly Mars volcanoes, largest volcanoes in the solar system. And with us is a volcanologist, planetary scientist, who's a senior scientist at JPL, has been involved with the outer solar system missions, Galileo and Cassini, has studied volcanoes throughout the solar system, including Earth and elsewhere. Please welcome Dr. Rosaly Lopes.
Thank you. Okay, thank you so much. I was asked to talk about the volcanoes of Mars, even though I'll start with a disclaimer that these days I'm not actually one of these people who studies Mars all the time. I actually study the outer solar system, but that's another story. So, what can we tell you about Mars? Well, you have already seen, can we have the slide? You have already seen quite a lot about Mars and how Mars geology is really, really interesting. And one of the reasons it's so interesting is that it's actually Earth-like, somewhat Earth-like. Now, Mars has craters, mountains, canyons, dunes, river valleys, these channels, and giant volcanoes. Every planetary surface that you look at, every solid surface of the solar system, is an interplay of several geologic processes. And the main ones are tectonism, volcanism, which are internal processes, and then impact cratering and erosion, which are external processes. So the reason why the surface of the moon looks so different from the surface of Mars, for example, is just because of that interplay of processes. On the moon, you're seeing, if you compare it with the Earth, for example, you're seeing many more impact craters than on the Earth. Now, on the Earth, we had plate tectonics, we have erosion, so most of our impact craters have been erased and you can no longer see them. But the giant volcanoes, well, Mars has the largest volcanoes in the solar system, and here's a topographic map. I'm going to try to get this, not sure where the pointer is. Well, anyway, you can see the, like the pimples there, named, okay, oh, thank you so much. Sure. Named Olympus Alba Patera and Olympus Mons and Asclepius, Pavonis, Arcia, and then there are some other volcanoes elsewhere. These ones we call the Tarsus regions and the Tarsus Mountains, and they are really gigantic volcanoes. Now, volcanoes are in fact found in many places in the solar system. We have volcanoes on Mercury, Venus, Earth, Moon, Mars, and the moons of the outer solar system. In fact, these days I mostly study Titan, which we call the Mars of the outer solar system. But, you know, as long as the planet has volcanoes, I think it's really interesting. And this is what we call a fire fountain on Earth here in Hawaii, and is about 100, it's about 30 meters high, that 100 feet. So one of the cool things about studying volcanoes is that you get to go to these places. But volcanism is very important in planetary geology because it's the process by which planets lose heat. And as you know, we're going to see, volcanism can also be an enabler of life because you need heat and you need water in order to have life as we know it. So I'm going to back up to the Earth because there is a very important difference between the Earth and Mars, and in fact between the Earth and other planets in the solar system. The Earth's crust is divided into tectonic plates. Artist Michael Carroll made this drawing in which, you know, he actually drew here on these images of the Earth where the major tectonic plates are. And if we go to the next slide, here you see we have a lot of volcanoes and earthquakes on the Cascades. That's the ring of fire around the Pacific. So the Earth's crust is broken up into these tectonic plates, and we have the mid-oceanic ridges or the spreading zones, such as here in the middle of the Atlantic, where the plates are spreading apart and volcanic materials coming up. and the plates are spreading apart about the same rate as your fingernails grow. So it's slow, but it's there. And over here, the plates are coming together in what we call the subduction zones. Now, the Earth has plate tectonics, but one thing that's very interesting is that we have not found evidence of plate tectonics anywhere else in the solar system. We do find tectonics on Mars. In fact, Valles Marineris, this enormous valley, like the Grand Canyon, which would spread from one side of the US to the other. And here you can see the comparison. You know, the poor Grand Canyon looks really small compared to Valles Marineris. But Mars never actually got plate tectonics going. And why is that? Well, the main reason is probably because the crust of Mars is much thicker, about 3 times thicker than the average thickness of the crust of the Earth. So it probably tried, and maybe Valles Marineris is an example of a place where it really rifted, but plate tectonics never got going. So that gives us some important differences about the volcanoes on Earth and Mars. Now, if you don't have plate tectonics, in fact, you can make volcanoes bigger. Because, you know, on Earth you have a volcano, the hot material coming up from deep inside the Earth, but the plate is moving, like you see the Hawaiian Islands, a very good example. So volcano builds up in one place, but then the plate moves and starts building up in another place, so it never really gets that big. And on Mars we have these gigantic volcanoes. We see here, we see the Tarsus Montes. And here is a closer image of them. So Ascraeus is about 18 kilometers high, Pavonis is 14, and Arce is about 9. So these are really giant volcanoes. And what is their composition? Well, we think it's basalt, and that's based on a number of things, but including their shape. These are actually what we call shield volcanoes, similar to volcanoes in Hawaii. The solar system's largest volcano is Olympus Mons, 600 kilometers in diameter and 26 kilometers high. This is an image from Mars Global Surveyor. It has a big caldera, a series of calderas at the top, and it's got the scarp around the bottom. And here you can see in this image, just from the outer flanks here, a number of lava flows, very long lava flows. And Olympus Mons is kind of a larger version of volcanoes in Hawaii. And that's like a 3D view of it. And you can see the shape is that of a shield. And shield volcanoes, that's a name that came from Iceland, because there are shield volcanoes in Iceland, and they look like warrior shields on the ground. Some people think that they look like turtles. Well, you know, you can take your pick. One really interesting thing about Olympus Mons is this tall scarp, several kilometers tall around the base. And then there is a corrugated material, very kind of like mountainous material around it. And in fact, this was my first project as a graduate student. My advisor, who believed in the sink or swim approach, you know, he said, well, there's Olympus Mons. It's big. It's good to start with the biggest, right? And no one knows how that scarp formed or how that material all around it formed. So go figure it out. And I'll talk more about that later. But anyway, going back to Earth, Hawaii, this is an image of Mauna Loa. Mauna Loa, for those of you who have been to Hawaii, is a large shield volcano. So again, we think the processes that formed Olympus Mons and the other Tarsus volcanoes are similar to the processes that formed the volcanoes in Hawaii, including Mauna Loa. So you see some very long lava flows. If you actually go to Kilauea, you know, has been erupting for quite a long time, you might see things like lava ponds and, you know, certainly lava flows. This is what we call Pahoehoe flow, and this is what we call an Ah flow, and lava fountains if you're really lucky. But, you know, as Jim said before, we have not seen active volcanoes on Mars, it doesn't mean that, you know, there can't be some activity that might yet happen in the future, because with volcanoes you always have to be careful, you know, never say never. Olympus Mons, this giant shield volcano. Now this is an image from the European Space Agency's Mars Express image of the nested calderas at the top, about 60 kilometers by 90 kilometers. And this is a series of calderas. Now, volcanic calderas form when the material under the volcano is removed, either by, usually by volcanic eruptions, maybe explosive eruptions, or maybe just lava flows, and the top of the volcano is left kind of unsupported, so it collapses. And the fact that we had these numerous calderas on Olympus Mons shows various major episodes of volcanism in which repeated collapses happen. Back to what's called the Oriole material around Olympus Mons, if we can have the slide again. Oh, can't have the slide again. Oh yeah, okay, here it is. So you see that there are like these lobes of this fractured, rugged material all around Olympus Mons, and we hadn't seen deposits like that anywhere else. So as I said, my advisor told me to go figure out what they were, and in fact, what I did was I noticed some landslides at the bottom of the scarp here, and these were from Viking images. And I thought, well, what if these giant things were giant landslides? And I didn't know that that was a bit of a crazy idea at the time. But in fact, it actually all worked out. It turns out that if you assume that the volcano was extended a long way before the scarp was formed, so that this scarp was just formed by landslides, eating away those outer flanks. It turns out that the volumes of materials around here correspond very well to the volumes you would expect from that extended volcano. So that worked out well. Now, there are other volcanoes on Mars that are really interesting, and some data that we have had so much new data in recent years that we are learning more and more about these volcanoes. This is one of the Tarsus shields called Rosaly Mons. This topography here is exaggerated about 10 times, but again, it has a giant caldera at the top. But one of the really interesting things were these dark pits. These are craters, but these pits, you see these dark pits and how they have irregular shapes. And irregular shapes means that they were not formed by impact. And we think that these are the tops over lava tubes. And if you go to places like Hawaii, again, I'm not advertising for the Hawaii Tourist Board, but it's a cool place to go. You can actually go inside giant lava tubes. Now, lava flows often flow and form tubes. That is because the top of the flow crusts over, and the lava is a very good insulator once it's cool. So you end up with a tube that insulates the lava very well, and in fact, the lava is able to go great distances because it's inside these tubes. But, after the end of the eruption, the source shuts off, the material drains out, and you are left with this roof that can collapse. So often you actually get skylights, what we call skylights over tubes. Now, it's really fun when the material is still flowing in the tube, the lava, and you actually are walking around and you find one of the skylights and you can look down and see that hot lava. Just don't step too close. But this is really interesting. We actually have thought that lava tubes existed on Mars and as well as on the Moon, but to actually see these caves that now became known as the Seven Sisters, and they have cute names like Abby and Jenny. That's really fun, and we're learning more and more about these volcanoes. And this is, now we have close-ups of this Olympus Mons Scarp here from Mars Express, and this is from the high-rise images. And in fact, it seems that my old idea is still holding, which is very gratifying, because not many graduate students can say that their first paper, actually still gets quoted. The disadvantage of that is that people realize how old you are. So Mars, I think Jim actually, talked about how volcanic eruptions might trigger these floods. Well, if you have material, hot material coming up, and if you have ice or permafrost and rocks, the volcanic material can actually melt that and allow liquid water to flow. And in fact, we think that that is the kind of process that lubricated those landslides and enabled these giant landslides to form. Now, I've been talking about comparisons of Hawaii and how Mars volcanoes are similar to those in Hawaii, but in fact, there are different types of volcanoes on Mars. And, so if we go to Earth, you have volcanoes like Mount St. Helens that are very different from the Hawaiian volcanoes. They are very explosive. This is the 1980 eruption of Mount St. Helens, and put out a lot of ash. And the flanks of the volcano then get covered by this ash material. And these volcanoes have different shapes. They tend to be much more of the classic Fuji shape. I remember once looking at Mauna Loa from a distance with a bunch of tourists, and one of them said, "Doesn't look like a volcano." And the reason is that people like to think of volcanoes as these big cones, but in fact, they're not all like that. So on Mars, if we go to the next slide, we actually do find some evidence for explosive volcanism, and some other volcanoes like this one, Tirrena Patera, that, actually from these thermal measurements, it looks like they are, ash, and in fact from the morphology as well, and they have channels carved in them, and if you think about it, ash is a much easier material for water to carve than solid lava. So we have a variety of volcanoes on Mars. And when you're an Earth geologist, the first thing you want to find out is the composition of the volcano, the composition of the lava. That tells you so much. And here are some different types of volcanic rock. You might ask what makes one volcano be so explosive while the other one is what we call effusive, or it doesn't have explosions, it's mostly lava flows. Well, it's largely the type of rock. It's really two things. It's the amount of gas dissolved in the lava, and the type of rock. If the rock is basalt, we find lots of basalts in Hawaii. Basalts don't have much silica, well, SiO2 for the 5 chemistries in the audience. The silica forms very strong bones, so that makes it difficult for the gas to come out. And when the magma comes towards the surface, the pressure decreases so this gas can expand. Now, if it can come out easily, it just can kind of whoosh out and form fire fountains. Oh, I'm going over time, I'm sorry. But if it can't, then the pressure builds up until it explodes. So this is my last slide. And I'm not involved in the MSL mission, so I'm not going to talk about MSL, but there are a number of measurements it can do that can, on this dust that might be volcanic ash, that can actually find out more about the composition of the surface. And knowing the composition is really all around important for geology. We can't send geologists to Mars yet, but we can send robotic geologists. So thank you very much.
Thank you. We are running gradually, little by little, running behind schedule, so I apologize, but I don't think we will take questions. But I do want to thank Dr. Rosaly Lopes from the Hawaiian Tourist Board and JPL.